webinar right now. Okay, let's talk about this. What is noise? Noise is random in nature. There's no real rhyme or reason. There's no pattern to it. We kind of generally characterize it as unwanted. We don't want noise onto our measurement that kind of may disturb the controls and may disturb the actual measurement itself. Now, what could be the source of the noise? Well, it could be EMI, electromagnetic interference, radio frequency interference. A lot of times, those kind of interference are taken care of at the I/O level. So when you actual analog signal coming into the control system, it's actually taken care of there. But it still can creep in. Bad shielding, bad grounding, bad shielding. So 4 to 20 milliamp signals come into twisted shield loop pair. So the signals are twisted to minimize any kind of EMI or electrical interference. And they're also shielded, which is actually, if you were to take a look at it, it looks like a bit of a tinfoil wrapped around it. And that, again, is to further protect the signal. Now, that shielding needs to be grounded. So we need to take all that unwanted electrical noise and send it somewhere. And that needs to be done at the control system, not at the transmitter. So, and a lot of times I see that the shielding is grounded at both ends. That's not a good thing, because then you can get induction current going on. More often than not, measurement noise is caused by improper specification, installation, and maintenance. And again, I think if some of you have joined me before, I talk about specified, installed, and maintained. And that is typically the main reason why we have perhaps excessive noise within our signal. Now, another one also, measurement principle. Some types of measurements are inherently very noisy and do require some dampening because of the actual measurement noise. We'll explore that later on. So let's talk about noise itself. So I'm going to use what's called the 𝗦𝗡𝗙 toolkit. So what are we looking at here? So upper right-hand side is the actual time series, the actual data as I collected. Now, this is actually what I actually did there. I just used the random function in Excel and imported it. So, and you can see obviously here there's over 4,000 data points. I can zoom in if I want to, and there I just zoomed in, and you can actually see the actual variations of the signal right there. So let me zoom back out. The quadrant on the right, upper right-hand side, that's called the power spectrum. And here we did a fast Fourier transform. You can do a fast Fourier or full Fourier. And I'll explain to you here why we're going to need this to determine the degree of noise here. But first, I want to explain here is that the fast Fourier will calculate. Mr. Fourier said back in 1789, if I'm not mistaken, that any kind of time series can be reproduced by using a series of sine and cosine waves and adding them all up. So here we're actually dissecting it, and we're looking at it in the frequency domain. And here we're actually breaking it down to its fundamental harmonics. Now, it looks kind of strange here because you can see that it kind of crowds to the right-hand side. And that's because we in the process control world, we deal with cycles per second. We deal with very slow cycles. It could be 5-minute cycle, it could be a 20-second cycle, it could be a 1-hour cycle. So that's why we tend to plot it in seconds per cycle, which is the inverse of frequency. So, you talk to reliability people, vibration people, they deal in hertz. So what I'm going to do here is I'm actually going to change the plotting here, and I'm going to go linear frequency as opposed to linear period. And you can see here now all the frequencies, all the harmonics are all equally spaced. I'll explain that blue line in a minute. Down the bottom left-hand corner is something called the autocorrelation function. Now, the autocorrelation function, as the name implies, is how does the signal correlate with itself? And again, that's another measure of actually measuring the randomness or the amount of noise within your signal. So if I were to zoom in on this a little bit here, it is a normalized function between +1 and -1. The two horizontal lines you see there, those are called the limits of confidence. And those limits of confidence get more and more narrow the more and more data points we have. Statisticians love the amount of data. And you can see the little picket fences inside there. If they fall within the actual limits of confidence, we could say there's actually very, very little correlation going on. So as you can see here, there's actually no correlation going on. So it's another indication that the signal is random and pure noise. One last thing I want to explain to you here is the blue line. So the blue line is actually the integration of all the actual harmonics being applied, being present within the power spectrum. Now, there's a term called white noise. And white noise refers to when we actually see the color white, we actually are seeing all the colors in the visible spectrum at the same time. And so we can apply to that to the signal. Here we're seeing equal amount of harmonics all across the spectrum. And so we see a straight line being applied right there. So what I'm going to do next, so I'm going to actually go here and filter this data, because this is what dampening is all about, is actually filtering. And it's typically a low pass filter. So I'm going to choose a low pass filter here. And I'm going to do here, I'm going to filter it at 10 seconds. So keep an eye on what's going to happen here as I actually filter it. So let me undo this. So you can see here the variability numbers is 1.718. So when I filter it, I'm going to reduce, I'm going to eliminate, attenuate, I should say, some of the higher frequencies. It is a low pass filter. I'm going to filter it. And you can see here, definitely, the first thing you notice, the autocorrelation function now, we've taken away the randomness of the signal. And you can see there's actually some actual correlation within the signal. And the power spectrum, you can see here, we actually attenuated a whole bunch of the higher frequencies right there. And so so if I undo this now, and what I'm going to do now, and I'm actually going to change the plotting of the power spectrum to log-log. And why do we use log-log? It actually, we're able to handle a very wide range of data points, both in the x axis and the y axis, and plot it in a more reasonable fashion. At the same time, it makes exponential relationships look linear. So once again here, I'm actually going to, so you can see here, the power spectrum is relatively flat all the way across the full spectrum. And once again, I'm going to actually filter this again, bring this back down to here, to 10 seconds. And now you can see here, I'm starting to roll off over here. That means I'm actually starting to attenuate at probably a minus 20 decibels per decade over here. I'm attenuating, and I can actually then back calculate what the cutoff frequency is by observing where the actual cutoff of that loop actually is. So I'm going to undo that. So that sort of quick overview of what noise is all about. So as I mentioned, so we see noise, and we're going to put some dampening on there. And as I said, it's a low pass filter that will attenuate. Now, again, I want to emphasize, it does not eliminate, it attenuate. And so based on the frequency response, the cutoff period, or the cutoff frequency, the faster we get, the more and more those signals get attenuated. It has units of time, typically seconds, and you can apply it at the control system, or you can apply it at the transmitter. Where should you apply? Should you need it? We'll talk about that in a little bit. And so this is just sort of a display of what applying dampening actually does. So you can see here where I'm actually applying some dampening right here, and now the signal is a lot quieter. But really, is the noise gone? Have we actually eliminated the noise? And the answer is no. The noise is still there. We just choose not to see it. Why do we do this? I said most of the time, a lot of the time, is because we have the wrong either type of transmitter specified, not installed properly. Why do we do this? Because maybe, hey, I like flat lines. A lot of operators would tend to see flat lines, but there is a price to be paid for this. And obviously things look better, but are they actually better? Let me tell you a story about I was in a paper mill. Oh God, it must have been 20 years ago now. And I was asked to do some bump test on a control valve, flow control valve. And lo and behold, that flow took over a minute to settle out. And so one of the most important things there, I knew right away, because obviously we've all brushed our teeth this morning. You open up the tap, you don't wait a minute for the flow to come up to full flow. So flow controls are usually some of the faster loops in any kind of processes. And so I knew there was something wrong. I did check the dynamics of the valve. And incidentally, my next webinar is about control valves. And the valve was responding very quickly. I then took a look at the installation of the flow meter. And this is exactly how it looked. Anybody know anything about mag meters? Is that they're very sensitive to turbulence. So as the flow passes through, when it's flanged to an elbow, the actual elbow will create a lot of turbulence, which creates a very noisy signal. You could just imagine possibly that the piping person calls up the instrumentation person and says, you know what, I'm just drawing up the drawings for the piping. How much of a gap do you need for your mag meter? And the instrument person says, well, I need probably maybe 35 centimeters. And and then lo and behold, the piping's all installed. And we walk up to the instrument guy walks up to the piping and with his mag meter, and that's what he's got. So a lot of times, bad process design creates a very noisy signal. And this is actually, you can see on the left-hand side where this is the actual true signal following a step change. So the blue line is a command signal to the valve. This is what I usually do when I troubleshoot and tune control valves. I do bump tests. And so the yellow line is the actual flow, but what we were perceiving was the following bump, where you see it took a lot longer to actually settle out. So signal, a lot of times, signal damping, filtering, whatever you want to call it, actually will hide flaws in our design. Now, what is the price to pay? I mean, there's no free lunch here. There's no free lunch. And the price you pay is that how you tune your control loop, how fast you can tune your control loop, is directly dependent upon how fast your process naturally reacts. So by putting excessive amount of dampening, we're essentially slowing down our process as perceived by the PID controller, forcing us to actually slow down our tuning. And that is the price we pay. So once again, there's another display here of a faster unfiltered response versus a slower filtered response. So I'm going to show you a demo here on that I actually developed. So what do we look at here? So this is based on our 𝗪𝗓 DCS, just a very simple simulation here. I've used these for other webinars as well. So here I actually have a controller. So the yellow line is the actual PV to the controller. There's actually a few other signals behind it. The blue line is the actual command signal to the valve itself. And I'm going to do a bump test. So I'm going to do a bump test and go from 40 to 50%. So there's my step change. And what I'm going to do, I'm going to zoom in on this a little bit more so you can see a little bit better what's going on. So now the yellow line is the actual process. The green line is reacting on the same signal, but now I've actually added 5 seconds of filtering on it. And then the white line has 12 seconds of dampening. And I think you can see very clearly here that the yellow line, the true process, is reacted. But now if we add more and more filtering, you can see how we are slowing down our process. So what else can we do here? Let's say I can actually add some dampening to the controller And as I mentioned, we can add dampening to the controller at the transmitter or at the DCS. Here, I'm going to add it at the DCS. I'm going to add 15 seconds of dampening. So now I'm going to go back to here. And what I'm going to do is I'm going to do an equal bump test down, back down to 40%. And now what you're going to see is that the yellow line is actually lagging behind the other two. I've actually slowed it down. It's actually even slower than the other two filtered signals right there. And it's obviously reacting a lot slower. So what else can I do? I can actually add some noise to this. And I'm going to add 5% noise. Again, inside the delta V, we have a noise generator that we can add. And you can see here that there's actually, let me go back to 15 minutes here. Maybe I filter, there we go. So I've added, 5% noise, and everything looks pretty calm because everything's filtered right now. So let me just bring this down a little bit. I'm going to bring this probably down a little bit more just so we can actually see. So now what I'm going to do is I'm actually going to set the dampening, originally set at 15 seconds. I'm going to set it to 0. And now so you can see here, there is actually a lot more bouncing going on. So that is a true signal. The other two are actually filtering. You can see the white line here actually, because it's actually filtered the most at 12 seconds, barely reacting, and the one at 5 seconds reacting a little bit right now. So you can see here, again, what I want to demonstrate, the more dampening you put in, the slower you're actually slower the response you're causing on your PV, on your process, and therefore the consequences is going to force you to slow down your tuning. So I'm not saying we should never. I always kind of discourage the use of dampening. I need to see, because obviously we want to reveal all the warts, all the flaws out there, because then we force us to actually address the situation. But there are situations sometimes where perhaps we do need a bit of dampening. And this is typically where any type of controller where the lambda tuning rule yields a high controller gain. Now, high controller gain typically is for level controls, tend to yield a higher controller gain and a slower acting reset. And a lot of times, especially in tanks, we'll use a pressure measurement to infer the level by measuring the static head. You could see this if it's an agitated tank. You see this a lot probably in pulp and paper industry, where the agitator is actually right in front of the level transmitter, causing pressure pulsations. What's going to happen then is that the signal will be noisy, and because of the high controller gain, the PID will react to that noise, and there's no value at reacting to that noise. The idea here is that, and then the valve is going to move a lot back and forth, and we probably will prematurely wear out that control valve. So putting in a little bit of dampening on controllers that have high gains may not be a bad thing. We don't want to take away from the signal. We want to just eliminate the noise so that the controller does not react and we do not prematurely wear out the control valve. Now, I mentioned before also there's other types of controllers out there, transmitters out there that inherently have noise because of their measurement principle. And this is one of them here. This is a nuclear sensor. This is actually using, probably on this side, this is used a lot can be used in pulp and paper. It's used in different places. I've seen a lot in the mining industry to measure the density of the slurry passing through that pipe. And so on the right-hand side, what you see is a nuclear source. Probably here it's going to be strontium-90, a pretty strong source. And on the left-hand side is a detector. And so the strontium source will actually emit beta particles, electrons, pretty powerful because it has to make its way through the pipe, through the slurry, through the pipe again and then get detected on the other side. And the more beta particles that get absorbed, the more dense the slurry is. And that's how we infer it. But because of the random nature, the completely random nature of the emission of beta particles, they will be noisy, and they do have to be quite heavily filtered to get a relevant signal. So how much is too much? Typically, you tune a control loop using lambda, using some sort of closed loop dynamics. You want to put as little as possible. We recommend that whatever speed you actually tune your PID control loop, that any kind of dampening should be 1/10 of that speed. We want to keep it as low as possible, so therefore we don't take away from the signal. Now, as I mentioned, you can actually put the dampening at the transmitter or at the controller. And the idea here is that if you are going to use it, put it in one spot and one spot only, and put it where it should be the most evident and the most clear, and everyone can see it, and that is in the control system. Try not to put it at the transmitter because it can be kind of cumbersome. It is more hidden. If you want to know if there's dampening at the transmitter, a lot of times if they're smart, you got to get either AMS to go look at it, to pull it and to pull up its configuration, or you need a 475 or a Trex heart communicator to be able to pull that off. Not as clear, not as evident. So if you are going to use a bit of dampening, I would suggest put it at the DCS or PLC control system. How rampant is it? Well, if you recall, some of you may recall, I've developed a Lakeside tuning index and a few years back, and I've been using that information of over 5,000, almost 5,000 PID blocks. And I've actually looked in a query my database to see how many of the PID control loops have PV filtering, the dampening and delta V, at greater than 4.9 at 9 seconds. And 9% of the control loops, almost 1/10, 1 out of 11, actually have what I consider excessive amount of dampening. By industry, food and beverage, 30% of the loops actually have excessive amount of dampening. I don't know what that says about food and beverage, and pulp and paper as well. A little bit surprising there that they do actually, 20% actually will use excessive amount of dampening. By loop type, not surprisingly, flow control is there, because flow measurements, every single type of flow measurement, with the exception of the Coriolis mass flow meter, all other type require a stable flow profile, which means that a proper process design, installation design is required to get the maximum out of your flow measurement. Now, level control, I'm kind of surprised by that. But then again, perhaps just what I talked about is that level control also yields a high controller gain. So may require a bit of dampening, as I said, to actually reduce any kind of output excursion that can wear out your valve. So is it noise or is it music? We're finishing up now. You know, we must take care of the noise and measurement noise at the source. I've talked about this before: specified, installed, and maintained. And if we don't do those three things, we're going to have a bit of noise in our signal. And so we need to take care of it so that our controllers can actually hear the music. So that concludes this. It's a fairly quick one today. My next webinar is May 12th. It's talking about control valves. We're going to talk about problems with control valves. We're going to talk about CV curves, delta P across, different types of valve, butterfly valves, ball valves. I certainly hope to see you there. Now I'm opening up for questions, and as you know, there is a 10-second time delay. I will answer your questions. You can answer them through the Q&A box or even the chat box if you want to. It's up to you, and I will pause and hope that I get some questions. Don't be shy. So I do have a question here from my experience. Do you see load cells weight transmitter being noisy? That's a great question, and I'm not sure exactly. I don't have load cells. It depends on the application, I would think. And I'll be honest with you, I don't have a lot of experience on load cells, but I can certainly see them being noisy if they're subjected to, if they're not installed properly and subjected to process design. Load cells are typically our piezoelectric type of material, where if you bend it or squish it, the actual resistance will change. So if your application, if you're loading it and the way you're loading it is actually can be a bit noisy as you load it, I can certainly see that signal being noisy as well. Excellent question. Another question, what is the difference between filtering and dampening? They're interchangeable. It's actually the same thing. So PV filtering, dampening, they're actually interchangeable. So therefore, one or the two, they're the same. So another question, how do you decide when to dampen versus changing the measurement device? Again, it's probably a case-by-case method. You can't just say, well, okay, that transmitter looking in the wrong spot. Let's shut down the entire process and move it. So sometimes you may want to just to mitigate the circumstances until you actually have a chance to properly fix the situation, fix the installation. Maybe a little bit of dampening. Just again, as small as you can, so therefore you don't destabilize the process and you don't mask the process. You let your controller hear the music and not the noise. Excellent question. Another one, so what would you do if you had a very high signal noise on the flow loop due to process problems or installation that cannot be easily resolved? I think I kind of answered that again. You probably put as little as possible on there to make sure that you're not masking the true signal away. If you put too much in there, as I explained, you slow down your process, but at the same time, you're masking the problem, and it will likely never get addressed right away. So another excellent question. Another one, have you seen signal noise in Coriolis meter output where when they were installed in series? In this case, it's just a flow measurement, no process control. What actually probably the main situation with Coriolis flow meters is two-phase medium. That can cause it to be noisy and erratic. So two-phase medium, meaning that because a Coriolis flow meter is essentially measuring inertia, mass inertia. And if your fluid passing through may have bubbles in it or air gaps or gas gaps inside where the density, the mass changes very rapidly, that will cause a signal to be erratic. So once again, we need to understand our process to make sure that we apply it properly, and therefore we can actually get a good signal out of it. Those are all excellent questions. So I do have a chat here. So let me see. So the question, how do you decide when to use dampening and further tuning of a loop? Once again, if I can tune my control loop to get with minimal amount of dampening, if no dampening, and the tuning actually does not react to the noise, then I will choose to actually not use any dampening at all. You heard me talk about level control. Level control tends to yield a higher controller gain, and higher controller gain will then react to measurement noise. But lambda tuning control for self-regulating processes like flows, for instance, tends to yield a lower gain. Now, a lower gain makes it impervious. It ignores the noise and actually reacts more to the actual true signal and does not react to the noise itself. So a lot of times, like I said, I will try to not use dampening and just try to see the true dynamics. And I will put in just enough to make sure that any kind of measurement noise does not destabilize the PID operation. Those are all excellent questions. Thank you very much. Still more time for questions. I'll give it another minute or so. There we go. Is a software tool when demonstrating noise and filtering freely available? It is it is available, but not freely. If you're interested, you can contact me, and then we can discuss that a bit more. That 𝗏𝗡𝗏𝗘 toolkit is my main go-to tool when I actually do troubleshooting and then process analysis of when I go to site. So it does. That's a time series part. Analyze is also a data collection part, and there's also a tuner part as well. Like I said, I'll give it a few more minutes. Thank you very much for all your questions. This is excellent. Just to let you know as well, at the end of this, you'll be sent an evaluation email, and really would appreciate it if you can all fill it out. We're always striving to improve ourselves. So another question: what will we use as initial filter time? 10 seconds, as in the presentation, or some other value? Once again, as low as possible. As little as possible. Do not start at 10 seconds. That was for demonstration purposes only. As little as possible. I think some of the flow meters may come at a default of 3 seconds. That's the borderline for me. As little as possible as you can to make sure, again, you get to see the true dynamics there. Those are excellent questions. Any other questions? Like I said, I'll give you another few minutes here. Another question: can we identify the source of noise by its characteristic? That's an excellent question, actually. I guess you could, yes. It depends on the frequency response. And now, if you see a lot of, I'll give you a story once where I actually was collecting data right off the 4 to 20 signal off the dropper resistor. So I'm actually collecting data using my data logger right off the actual Agnall signal. And I kept on noticing some really high frequency noise, and the faster and faster I sampled it, the more and more clear it became. And then I actually ended up identifying it as a 120 hertz signal. And so the 120 hertz signal. And what we ended up determining was that all the signals were coming into this one analog input card, and all the signal, as I mentioned, needed to be grounded properly. So we noticed all the shields were all grounded properly at the control system, not at the transmitters. But however, they all went to ground, but was the ground grounded? And lo and behold, it wasn't. We followed that big green wire all the way down the tray, the wire tray, and it actually was not connected to anything. So the ground was floating. So in that instance, we determined obviously that it was an electrical grounding problem, and all we had to do is just properly ground it. Again, if you're going to do, I mean, grounding is a lost art, it's a lost science, but we ended up building a actual proper instrumentation ground, not an electrical ground, and where all the instruments were grounded, and just to stay away from electrical noise. Another question. So you would set filter to 0 seconds or none by default and only add filtering if needed? Absolutely. Yes, definitely. You want to start with 0 first to make sure that you see the true dynamics. The one exception there is probably the nuclear example where it's expected. Listen, it's expected it's going to be noisy. You may want to start small and then slowly increment until you get a usable signal. But other than that, I certainly would keep it at 0. Definitely. Keep the questions coming. That's excellent. All right, we'll go for another minute or so. Here's another question. So the question is, and this, oh my God. So when do you use D action on PID control? And you do add D action, do you add dampening to PV? That's okay. First of all, okay, using D action. So for those of you, uh, actually, if you, what I can do is I can send you the video of my previous webinar where I do talk about D. And one of the first things I say about D, and I ask people, what does D stand for? And people say, well, it stands for derivative. Actually, in delta V, they call it rate, but it's PID derivative. And I say, no, it stands for don't. It stands for doom, and it stands for disaster. So actually, in my Lakeside tuning index, I found that about, I think around 10 or 12% of the loops actually have D in it. It doesn't necessarily mean that they should, but they do. Next part of the question, when do you use D action on PID? It will be typically on high inertia types of processes. The most common type is temperature control. And temperature control tends to have a very clean signal. Temperature signals are not typically noisy, and therefore, because they're high inertia and because they're clean signals, you can use derivative action. There are other probably very specific types of loops where you could use derivative, not necessarily where you should, but you could use it. Now, and derivative is also will move the output proportional to the rate of change of the PV. And you can imagine if you add a lot of noise onto that PV, we characterize noise as high variability. The derivative will act upon that noise and most likely destabilize the entire process, the entire PID action. So therefore, it's not advisable to use D on any kind of noisy signal. However, most PID algorithms at the D part, the D portion, actually include a first order filter for that particular branch. And what they're trying to do is to compensate for what I just described before, where they're trying to eliminate or attenuate some of that high frequency noise prior to the derivative action until it goes to the output of the controller. So excellent question. Keep the questions coming. Like I said, we'll go for another few minutes. This is great. You guys are asking a lot of great questions. All right, like I said, we'll give another minute or two. Okay, we'll go to 11:49 my time, and then once again, there's my contact information, and I certainly hope to see you next month. A webinar on control valves. So I have another question. Would it be all right to use D when the control output changes are too fast? And it's the opposite, actually. If the output changes are too fast, you probably may not want to use derivative at all because if it depends on what you mean in terms of you saying if the control output changes are too fast. If it's too fast because it's reacting to noise, then derivative is certainly not your friend in that case. And in fact, if you're using on high inertia processes, derivative is actually good at putting the brakes on, allowing you to probably reach or recover faster from a low disturbance, but actually put the brakes on when you're approaching set point. A lot of derivative. There's always a lot of questions about derivative. And like I said before, D stands for don't, doom, or disaster. Okay, one more question and then we'll wrap it up. All right, it's 11:50. If you do have additional questions, if you think of something afterwards, you're more than welcome to reach out to me. There's my contact information on your screen. And really appreciate you attending. And I certainly hope it was informative. And like I said, we'll be sending out an evaluation email in a few hours. Always looking for feedback. Any feedback is good feedback for us. And certainly hope to see you on May 12th. And thank you very much for attending. Have a great afternoon. It's a beautiful day out there. Enjoy your time. Thank you.